Okay, thank you very much. Hey, g'day everyone. Ladies and gentlemen, thank you for joining me to talk about fatigue. And fatigue's often a really interesting thing to talk about. Everyone knows what fatigue is, or do we? So let's actually start talking about fatigue, but from the perspective of how something fails. And for those veterans of my webinars and podcasts and courses, you might recall this example I often show when I talk about which I use to illustrate failure. This is a Xylon bullet-resistant vest. Xylon bullet-resistant vests were manufactured by Second Chance Body Armor, a company that sourced Xylon fibers from this Japanese company called Toyobo. Now, Xylon sounds a lot like nylon because it looks a lot like nylon, just that it's incredibly strong, much stronger than nylon. Yeah, so it's a fiber which gives us incredible strength. And if you've ever had anything to do with bullet-resistant vests or bulletproof vests or whatever you call them in your walk of life, there are two main types. Ones which are exclusively made out of fibers, which can even flex and allow you to pass through, which is very important because if you've ever worn one of these things, you'll realize how hot you can get on the inside. And the other types are ceramic, which don't move, and they're usually in the form of plates that you insert into a vest. They have limited ability to cover the entirety of your body, but because they're ceramic, they have a lot more a lot more characteristics which are naturally more useful at stopping around from going through said vest. Now, unfortunately, these Xylon vests, which were then issued to usually law enforcement officers across North America, one unfortunate police officer was shot at and then was struck with a 40 caliber round, and it actually went through. The officer ended up being fined, but obviously it was a concern that the vest didn't stop a round. It was designed to stop. And it turns out that when they investigated that particular vest, the fibers were 30% weaker than what they should have been. And when they said, okay, this is a problem, they then started looking at all the other vests that had been issued to police officers across North America. When they tested those vests, all based on Xylon, they found that 58% were penetrated by rounds they were supposed to defeat. 38% had excessive back face deformation in that, although the round did not get all the way through, it was created a shape or impacted the wearer to the extent that would have caused significant injury. And only 4%, or 1 out of every 25 vests, were okay. So something was going wrong. And to understand why things were going wrong, let's look at how bullet-resistant vests are supposed to protect you. So you can see bullet-resistant vests, which are based on fibers only. They essentially layer upon layer these really, really strong fibers. And when the round hits the vest, there's this initial impact and mushrooming, which is very important. You are trying to deform the round so that the force is exerted over a wider area, decreasing the pressure. And ceramic plates are really, really good at doing this. Ceramics are incredibly hard. Fiber weaves, not so much. They only deform the incoming round to a certain extent. But after they have deformed, then the round will essentially create a shear plug where layer upon layer of fiber weave essentially join or fuse with the front of the round. And then energy is lost, which is what we want, by shearing and local fracture. A shock wave is created, which then reflects through the fiber weave. And eventually, what you want to have is broken fibers, delaminated fibers, yield and fracture, where all the energy that went into breaking those fibers essentially stops that round from getting through. So you really want very, very strong fiber. And Xylon fibers are about as strong as they come. So here you can see a chart where you have specific modulus on the horizontal axis and specific strength on the vertical axis, and lots of data points which essentially tell you how strong something is with respect to its mass. And on the top right-hand corner, you can see PBO fibers, which stands for polyphenylene benzobisoxazole fiber, which is the proper name for this type of fiber. But Xylon is the commercial name for that particular fiber. You can just see how much stronger it is compared to different Kevlars and steels. bottom left-hand corner. There's incredibly strong fiber. So polyphenylene benzobisoxazole fiber, you can tell that I use this example a lot because I'm pretty fluent at that particular name, is woven in a really, really fascinating way. Each fiber, which is very, very small, is itself made up of lots of smaller, almost microscopic elements. The fiber itself has lots of little microfibrils, and the surface has it's a sheath that goes around, very similar to abseiling rope. And these fibers are based on a polymer. And a polymer is a really, 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 really long molecule with thousands upon thousands of atoms all joined together using covalent bonds. Problem with Xylon, though, is that NASA identified aggressive hydrolysis. And hydrolysis is a fancy word for reacting with water on PBO fibers in 1996. So a good 7 years before that first vest had a round to go through it. Now, if we zoom in even more onto the actual molecule itself, a mer is a repeating unit in a polymer chain. And this is what the mer for PBO fibers looks like. And in the heart of this mer are 5 atoms, a 5-atom ring called the oxazole link, which contains 3 carbon atoms, 1 nitrogen atom, and 1 oxygen atom. And the problem with this little link is that when water molecules come into the picture, well, the first thing that happens is that the water molecules react with the oxygen part of the oxygen atom, and then they react with the nitrogen atom. And what that means is very, very quickly, we have a broken polymer chain. So this is where water will essentially attack the strength of PBO fibers. So you might ask, why the hell are we using PBO fibers in the first place? Well, manufacturers can claim to put water-resistant or waterproof sheaths or protection around fibers, therefore mitigating the issue. But of course, you need to be really sure that surface coating, is working. Anyway, so of course, these were some concerns that this was essentially the most well-known way PBO fibers can fail in the presence of water. So they started testing Xylon fibers from the manufacturer, and they put these fibers into chambers with had absolutely no moisture in those chambers. And over almost a period of a year, they tested the strength of these fibers where there was virtually no access to any water or any moisture, and the residual strength appeared to be pretty constant. If there was a downward slope, it's very slight. You can see it on the screen right now at elevated temperatures. However, when they did the same test on other fibers in moist environments, you'd see the strength decrease very rapidly, and the strength stopped decreasing, and they took a lot of the moisture out of the chamber they were testing. And problem with that for second chance is that they didn't test for the well-known hydrolysis. And in fact, they got some field data which they ignored in 2001, and eventually they had to declare bankruptcy when they realized that all their bullet-resistant vests had to be recalled, and essentially Xylon is now banned from use in bullet-resistant vests, and Toyobo paid $66 million to the United States federal government, and there was 1 known death from faulty Xylon vests. Now, I often talk about this in the context of trying to find the root cause of failure. And one of the reasons I do this is because a lot of people will say, well, the root cause, of course, of failure was hydrolysis. Hydrolysis is the thing that caused this thing to fail. The problem with that is that is a physical or natural phenomenon. It's a physical phenomenon. You cannot legislate out hydrolysis. Hydrolysis will be here tomorrow. It's going to be a concept that remain until the laws of this universe somehow end in perhaps whatever scenario physicists predict several billion years from now. But the reality is, when you are looking at the root cause of a problem, it has to be something you can address, which means it has to be a human behavior, a choice. And so the root cause clearly in this scenario wasn't that this is some physical phenomenon that we allowed to enter our system. It was the fact we allowed it to enter our system, our design. And so it's very important to understand what a root cause is and understand why things fail. Now, just bear with me for those people who said, that's all good, but you promised that you're going to talk about fatigue. So let's get to why we're talking about hydrolysis in the conversation of fatigue, in a conversation about fatigue, starting with the question with the phrase why things fail. So as reliability engineers, we want to know why things fail, not to admire them. Some reliability engineers pretend to be reliability engineers by admiring problems and writing reports and maybe fitting curves, et cetera, et cetera, et cetera. But we are primarily interested in understanding why things fail in order to prevent those things from failing in the future, i.e. improving reliability. So let's visualize a failure event with an apple. And the idea of good reliability engineering is to work out what we need to do to stop things from failing. And one of the first things we need to do is start by defining what that apple is. What is failure? Because if you want to know the causes of failure, you need to actually understand what those failures actually are in your system. So failures. A failure is any event where a system inherently ceases to perform specified or required function. Now, if your computer stops performing a function because the electricity power being provided to your computer disappears, perhaps as a blackout, your computer hasn't failed because it hasn't inherently ceased to perform a specified or required function. It's when the function that you ask your thing to provide, for whatever reason, the product says, I can't do that anymore because my capacitor is now on fire or something similar to that. And so to understand what a failure is, you need to know what a function is. Functions are behaviors, processes, actions, or tasks that support a requirement. And they are very closely linked to this concept of specification. Specification is a detailed description of a function that supports a requirement. So in a way, a specification and function can be somewhat seen as somewhat analogous to each other or synonymous. Specification is essentially a very well written out function to support this thing called a requirement. So what is a requirement? Well, a requirement, at least in this conversation, is a condition or capability needed by a user or customer to achieve something. Now, no doubt there are lots of systems engineers out there who say, no, 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 according to this handbook, paragraph 3, sub delta, whatever, a requirement is this and a specification is that. But in the context of this conversation, I want you to look at requirements as the language that a customer would use in order to explain what they hope to achieve by through using your product, your system, your device. The specification is more analogous to the language engineers or designers and manufacturers would use to describe what the thing is supposed to do. And the idea is that specification and functions are drawn from the requirements, what the customers or users would describe what they need to be able to do, where the specifications and functions are how engineers would describe what they need to design. Functions are what the item is intended to do. We know there's lots of different devices out there which can provide the same, which support the same requirement for a customer or user, but use fundamentally different technology to get there, and therefore have very different functions or specifications as designed, as described by the engineers trying to support that requirement. But once you have that worked out, you can work out what the failures are, because those failures are drawn on the, but defined as the event where your thing stops functioning, so to speak. And if you've got this chain right, you will be able to link a failure back to a negative impact on a customer or user. But of course, there are functions and then there are functions. Not all functions are the same. One of my colleagues or one of our friends, he first introduced me to the idea of breaking functions down into 3 different groups. The first one being basic functions. There's a reason why. Basic functions are the obvious functions. They provide baseline performance. These are sometimes the only functions engineers focus on because they're seen as the most important functions. But essentially, basic functions are the functions that allow your device to be categorized as a clock or a car or a toaster or a watch. Basic functions essentially allow you to call your thing by a noun that you would hypothetically use to categorize how you'd sell that thing on Amazon. It's a microphone, it's a speaker, whatever it is. Basic functions, the baseline functions, which seem so fundamental that we often think are the most important. However, in addition to basic functions such as contains, maintains flow rate, calculates, secures, transforms, and plenty of others, we now need to also brainstorm or think about these things called interface functions. How components within a system need to interact with each other in order to work. Very well-known examples include many NASA, European Space Agency joint projects where NASA control systems output data in terms of imperial units like foot-pounds, whereas European Space Agency uses a lot of control systems where they're supposed to have that data input in terms of the metric system. So a lot of things have impacted the things like the Martian surface at a great rate, and not simply because those control systems did not interface with each other very well. And as a rule, about half of all failures occur at interfaces. And so these functions, these interface functions include the fit functions, and they are also the easiest way to drastically improve or destroy reliability. So there's interface functions. But now there are the, before we move on, some examples include provides power to, or a power supply, connects with, transmits torque to a gear set if it's an electric motor, inputs data into, along with those units of measurements I just talked about, does not exhaust heat onto, to make sure we don't have an exhaust manifold ruining the day of your PCB, and of course, plenty of others. And the last category of functions are those additional functions, the things that may essentially allow customers or users to decide if your thing is a good product or not. So a bad product is a product which just has those basic functions. A good product is a product that has those basic functions and a whole lot more. That includes form functions. Does it look good? Is it safe? Is it easy to use? Is it easy to maintain? Is it comfortable? These are all additional functions which a lot of engineers often think are not nearly as important. Well, if you do that, you're just going to essentially focus on designing a behemoth or a monstrosity, which, yes, is technically a product, it's technically a bicycle, it's technically a child seat, but if it's difficult to use, if it's not comfortable, if it looks ugly, if it's not safe, if it's really difficult to maintain, if it's not easy to use, etc., 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 it's a bad product that no one will buy. So examples include ensuring that all fasteners require a single tool. That is, you don't have 65 different bolts, it's 65 different size ratchets required to adjust each one. Is it childproof? Does it have modular skins to allow the aesthetics to be easily changed? Does it have interchangeable left and right hand grips? Does it comply with environmental regulations? And of course, plenty of others which make a product a good product. And so the reason why we often have these three categories of functions is that it helps us to brainstorm all the different ways we could perhaps make an unreliable or crummy product, I should say. And these functions sometimes require inputs, and it's often useful defining these inputs because, again, these help with the system to external environment interface considerations. Things like energy are a huge one. How clean does the power supply need to be for your CNC machine to work? If there is a slight deviation in voltage or current, will that destroy your CNC machine? If you want to sell your CNC machine across the world where power supplies are of, let's just say, different qualities with different levels of cleanliness or dirtiness, then getting on top of that could save the day. Now, these function categories are not from standards or textbooks. They're only here to help you brainstorm, and I have found them very, 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 very useful over time. And again, I can't claim that to have invented them myself. Carl Carlson he first shared them with me a fair while ago, and I'm not sure if he invented them or if he was passing them on himself, but I'll have to give the credit to him, because I have found they've been really, really helpful thereafter. So they help you brainstorm every facet of your system. After we have brainstormed the basic functions, and it's a really useful, then we say, okay, no more basic functions, let's brainstorm interface functions. Okay, no more interface functions, let's brainstorm additional functions. And all of a sudden, you have a very, very robust list of functions to make a wonderful thing. But of course, we're here to work out why things fail, and that's why brainstorming is here in the first place. We're either trying to work out why something has failed, or we're trying to work out how something might fail in a hypothetical sense to ensure that we design those corrective actions out of the system or the product in the first place. So let's go back to our failures that we represent with apples. So each one of these apples is a failure event, and we can further visualize the failure process with a tree, because as we know, apples grow on trees. And each one of the apples represents different types of failures. So different types of failures, different failure modes. So for example, let's just say one of these apples represents something very bad happening, like the solder joints on an electric motor cracking and detaching, meaning that our product now no longer works at all. That's kind of a big failure. Maybe that's a high severity failure mode. So therefore, the apple that represents that failure mode is going to be very big and angry in this case, will make it really red. And perhaps if there's a 15 decibel noise limit on our electric motor, and it turns out that over time our electric motor now creates a noise that is 17 decibels, only 2 decibels higher than 15 decibels, that's still a failure, but you might argue that's a slightly less severe failure mode, a low severity failure mode. So the apple that represents that failure is correspondingly small. And so this tree is here to visualize failure. And of course, apples are wonderful, healthy fruit. So look at these apples as evil sort of vegetables that, wicked queens and nursery rhymes or nursery tales, or fairy tales, I should say, have used to poison people like Snow White. So these are bad apples. So what we want to do is understand what each apple represents for our tree of failure. Now, the reason why the tree of failure isn't a bad visualization tool is because we know that trees have roots, and we don't see the roots. The roots are sometimes very hard to see, and the idea is that this tree of failure has a root cause, which is supposed to represent some scenario or some event or something that then goes on to trigger the failure event. And that's how many engineers like to see it. But in practice, there is a whole combination of roots that's combined to create the scenario or circumstances that allow failure to propagate. And so while a lawyer would love to be able to work out the single root cause of failure. And when I say lawyer, I also mean engineers who are trying to apportion blame, love trying to find the unambiguously singular reason for something failing, especially if it's not in your department. In the real world, if you're trying to limit the likelihood of failure, you need to look at all contributing events, regardless of how close you think you are to that event chain, and see what you can do to contribute to all other efforts to reduce the likelihood of failure. So root causes are something you can do something about. They are not, for example, saying that the supplier had a design or manufacturing error. That's blame or avoiding responsibility. Why? Surely a manufacturing error could cause failure, but that's cool. Of course, that's going to happen. But can you do anything about it? If you're going to simply apportion blame, all you're doing is saying it's someone else's responsibility. And as soon as it's someone else's responsibility, as soon as it's not your responsibility, it by definition becomes an environmental consideration, because you're saying, I cannot influence that whatsoever. But true root causes include things like looking at what you have done, and maybe you put too much time pressure on the supplier, didn't establish a collaborative reliability strategy with the supplier. Perhaps you provided incorrect specifications to a supplier. if you look at what you can do to help address the likelihood of supply, design, and manufacturing errors, now you're in the game of improving reliability. If you don't believe me, look at what Boeing did. They are all about blame and avoiding responsibility. They weren't really interested in improving reliability, and bad things happened. And so while textbooks might say the root cause is the initiating cause of failure, in the real world, it's a thing we can change to make sure that failure hardly happens again. Therefore, it has to be a human behavior or decision. Can't be hydrolysis. Hydrolysis is a physical phenomenon you cannot outlaw or cancel. So many root causes look like these people. And again, some of the veterans from my webinars will recognize these people, these caricatures who I use to represent the enemies of reliability. On the left, we have the process zealot who doesn't care about reliability. She just wants to tick all the boxes so we can certify something as being amazing. In the middle, it's a ponderous professor who loves data and analysis, but really isn't interested in helping you make better decisions or having any risk in his reputation being put forward. He has to wait 3 years to do the analysis perfectly before he gives an answer. By then, you're already bankrupt. And the guy on the right is the infant manager who wants the wrong thing fast. He's wanting to get to the next milestone as quickly as possible, and therefore he is always putting downward pressure on the amount of time you spend doing reliability stuff. And so these three enemies often represent the root causes of failure in an organization. Now, there's a reason I'm torturing you with this meandering conversation regarding functions and root causes and failures, because once we have our functions, we can start to ask some questions regarding our thing, about what it is doing, what it's not doing, what it's not going to do. And those questions can be very, very useful. So one of the first questions you might ask if you're confronted with a failure, or if you're trying to ponder in a FMEA or fault tree analysis what your thing might not do in the future, is what is my system doing or not doing? What does failure look like? And then once you have understood what your system is doing or not doing in your actual failure scenario or your hypothetical failure scenario, then you can ask, why did this happen? And that question itself is broken down into three smaller questions. What does a broken bit look like? How did it break? What started it? And once you ask and answer those three questions, the next question you need to ask yourself is, what did we do wrong? The answer to that will be the root cause. Or a more positive spin on that question is, what do we need to do moving forward? And so if you start at the very top, what is my system doing or not doing? Perhaps in a FMEA or a fault tree analysis. The answer to this question is what we call a functional failure mode. It is the functional consequence of a failure mechanism. There's tons of examples that are about to be bombarded on your screen right now. So this is how you would explain what your system isn't doing anymore for you to classify it as being failed. For an HVAC system, maybe your HVAC system isn't heating your office at all, or your HVAC system is heating, but not with a lot of power, so it takes a long time to get to the desired heat. Or maybe your HVAC system is heating okay, but it's making a ton of noise when it does it, etc., etc., etc. So these are all different things, different ways of explaining why your HVAC system isn't working without actually saying anything about the technology or why that is happening. And the reason why it's really important to go down one layer at a time is you don't want to miss stuff. And so what is my system doing or not doing? The answer to that question is the functional failure mode, the functional consequence of failure mechanisms. Leakage, or it disengages, or it slips, or it's an inadequate or poor performance of a function. Once you have the answer to that question, then the brainstorming can move on to the next part of this question sequence, which will take us to, what does the broken bit look like? The answer to that question is what we call the physical failure mode. It's the physical consequence of a failure mechanism. And so if the HVAC is not working, then it's going to be, you're going to have a component or element of it, which is broken and doing something it's not supposed to do. So maybe a shaft is fractured, maybe something is loose, maybe the refrigerant is contaminated, Maybe something is worn, maybe something is deformed or cracked. This is what the broken bit looks like, which is a physical failure mode. And these things are then going to, in your causal chain, be potential explanations behind your functional failure mode. Next question, how did it break? The answer to that question is the failure mechanism, the physical, chemical, electrical, thermal, or other process which results in failure. Now, many of you might be fatigued by this meandering story to get to this point, but it's really important to understand what, for example, fatigue is. And fatigue is a failure mechanism. Often people think fatigue is something that is essentially the entire failure event itself. And of course, it can be something we need to put a lot of thought into, but fatigue is a failure mechanism. You need to understand, we need to understand the failure mechanism to find the root cause. And I can see Carl's asked a question. I'll come back to that in a minute. The failure mechanism also just drives how you maintain your thing. Your maintenance regime, your preventive maintenance regime in particular, has to be based on a failure mechanism. It's also the only thing you can model. This will help you understand how long your thing might last. And that hydrolysis of our bullet-resistant vest at the start of this conversation is an example of a failure mechanism. Here is another failure mechanism. When my computer decides to move on, there we go, tin whisker, where you have these infuriatingly thin, tiny, dead straight whiskers, often growing from tin-plated terminals in electronic equipment. And this, of course, when it goes from one terminal to the other, creates a teeny tiny short circuit, which can be a problem when keeping the electronic components in mind. Here is another example of a failure mechanism. You might be able to see there are some weird shapes on the screen right now. What's going on here is that you have a conductor on the left and a conductor on the right with the voltage difference, which essentially means one is the cathode and one is the anode. And you can see there's sort of these teeny tiny lightning shapes moving from left to right. These are called dendrites, where you have very small conductive pathways slowly marching across the chip surface. And when it does make it all the way across, you'll have another slow leak. Then there's corrosion. Corrosion is simply oxidation, but oxidation that occurs on metals. And it's oxidation on metals is a very similar phenomenon across lots of different metals. Some metals do not corrode, some do. Some metals like aluminum or aluminium, when they corrode, they create a protective surface, which is why they often look dull. And once they have that protective surface, it stops ongoing corrosion. Then you have metals like those based on iron, the steels, which can often corrode. And when they do corrode, there's nothing to stop corrosion after it starts. And eventually metals will be worn or eaten away by corrosion. And last but not least, we have fatigue. You can see Shafat has asked a question. It's a good question, and I'll get back to you in a minute. Fatigue is where we have cyclic stresses being applied to usually a metal. And you can see what's happening here is you have a metal in a test rig, which is being subjected to cyclic stresses. And what we're doing right now is slowing down the video because we have just reached the point where this poor old metal cannot take it anymore, and the residual part of the metal is not big enough to withstand the load. Essentially, the crack on the left-hand side has reached what we call a critical length, and then it propagates very, very quickly across the remainder of the metal. You can see the metal surface looks very different as a result, and our thing has failed. So fatigue is a really troubling failure mechanism because it appears everywhere in the world around us, especially when we have metals keeping things really, really strong. So here's a microscopic view of a fatigue crack. Fatigue essentially involves a crack which gets bigger over time due to repeated cyclic stresses. And so fatigue cracks have to start somewhere, and they start from imperfections. And we'll talk about those things that start these cracks a little bit later on. At the tip of a crack, you have what's called a plastic zone. The reason why you have this plastic zone at the tip of the crack is because the steel or metal on either side of the crack is offering absolutely no structural support to our material. Where all this steel, which is not touching the steel beneath the crack, essentially it transfers or requires strength to be provided from its neighboring atoms, and eventually you will have this point at the tip of the crack where the crack tip or the metal surrounding the crack tip is essentially providing most of the support to the metal above and below the cracks, because the crack itself is essentially severing any continuity in the structure, and therefore the crack tip has a lot of stress amplified. In fact, we use this thing called the stress intensity factor, which we often represent with the letter K, to try and describe how much stress is being applied to the metal at the very tip of the crack. If you imagine tearing a piece of paper, once you start the tear and you pull the paper apart, it is the tear that continues through the paper. And the reason being is because every time you pull it apart, the piece of the paper which experiences the most stress is at the tip of that tear, like the crack. And that's why you have a single tear going through a piece of paper once you start that tear. And that's very common phenomenon across a lot of materials. And we know that as the crack grows, or the speed at which the crack grows, how much longer this crack gets after each cycle, we know it's roughly defined by what we call delta K to the power of M. Delta K represents the difference in the cyclic stresses. So when you have a cyclic stress, you have a peak stress and a minimum stress, and the distance between those peak and minimum stress is the delta K. And we found through experimentation and some study of the process that that for most materials, there is some factor or some exponent M which describes how long this takes. And so that delta K represents cyclic change, and that power, that exponent, means we have a multiplicative effect. Now, for those long-suffering attendees of my webinars and conversations, you should know that would then mean that we expect the log normal distribution to describe fatigue. The log normal distribution is like the normal distribution, except that it is used in a way that is based on the premise of multiplying lots of random processes together. And whenever you have something where delta K is the power of M, you're multiplying this thing over and over and over again. And you often see the log normal distribution do a remarkable job of modeling the time to failure, or more correctly, the cycles to failure of steel. But that said, even though we're talking about a log normal distribution, there's a probability distribution, we often use those terms to describe things where we have small amounts of data. We actually have tons of data for fatigue because most steels are very, very well understood, because lots of the steel specimens are sent off to labs like this one, inserted into test rigs, where you can have cyclic stresses applied to these steel samples, and you can see here that we can see exactly what stress we're applying, the cyclic stresses. We're counting how many cycles we're exposing to our steel sample, and we can do this over and over and over and over again. And we found that if we do this over and over and over again, we could plot the times to failure on a very special chart that allows us to see exactly what's going on. So if we do these tests in these labs, when we can plot this data on this particular chart, we can start to see that for this steel, there's a clear pattern emerging. Now, there's something very important about this chart before we look at this shape anymore. On the vertical axis, you can see the stress, the cyclic stress, goes up uniformly, 0, 200, 400, 600, 800. But along the horizontal axis, the number of cycles in the way this chart is scaled at least goes up logarithmically. So 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, so on and so forth. So go from 1,000 to 10,000 to 100,000 to a million, 10 million, 100 million, billion, so on and so forth. Because reason we do this is because we have found that all that data, when plotted on this chart, creates a beautiful pattern, at least for most steels. Most steels have this sort of line that can fit our fatigue data. And if we get this beautiful straight line on the left-hand side going down, we get this other beautiful straight line, which is completely flat on the right-hand side. If and only if we create a chart where the number of cycles is scaled logarithmically. This is for 1045 steel. And the reason why this is very important is because this chart allows us to identify this thing called the endurance limit. That is the stress that below which we do not expect fatigue to occur for steel ever. So in this case, the endurance limit is about 300 megapascals. So if you have steel being exposed to cyclic stresses of 200 megapascals, you would not be ordinarily worried about fatigue. Aluminium or aluminum, on the other hand, it's very nasty. No matter how small the cyclic stress is, it's going to eventually fail, even though the cycles to failure will be considerably high. Nonetheless, aluminium or aluminum, even though it's still very light, has low density for the strength it offers, which is why we see it in planes a lot. Eventually, every one of those structural members will fail due to fatigue. So the vertical axis, which is stress in this case in terms of megapascals, we often just summarize or notate or represent with the symbol or letter S. The horizontal axis we represent with the letter N, because N is the first letter for numbers. And this creates what we call an SN chart. The SN chart allows us to, for example, work out the median, what we call fatigue limit for this 1045 steel at 400 megapascals is around 87,000 cycles. But remember, for SN charts, it's all about the logarithmic scale on the horizontal axis. And so when it comes to fatigue, we can use our knowledge of fatigue to help us understand how long it's going to take something to fail. So, for example, here is the door handle on a smart lock or any lock for that matter. The door handle is obviously going to be subjected to lots of cyclic stresses over the journey. And let's just say we're concerned about fatigue cracking from lots of door openings here. What we might be able to do is conduct finite element analysis in our preliminary design to work out where the stress is maximized. And of course, once we work out where the stress is maximized, we might be able to have a good idea of how much stress our handle steel will experience when someone opens the door. And our finite element analysis identified the maximum stress was about 500 megapascals, which means we can go back to our SN chart, look at 500 megapascals. In fact, we might even zoom in to get a better look at it. A 1045 steel, 500 megapascals, draw a line across. We can see that from this blue region here, which represents our 90% confidence interval. So these laboratories which did test after test after test after test created this region of 90% confidence, which means that we are 90% confident that at 500 megapascals, our door handle will fail somewhere between 12,000 and 30 cycles, all the way up to 63,620 cycles. Now, of course, this is in a logarithmic scale. So you can see the median best guess, which is 27,660, is a lot closer to the lowest guess of 12,030 or lower confidence bound than it is to the upper confidence bound, the 63,620 number. But if we look at the natural logarithms, you can see that the median logarithm is much more central to the other two confidence bounds, and that means that that's because we know, based on that whole log normal distribution conversation, and we expect to see the bell curve on these sorts of charts. Now, I can't fully explain why the log normal distribution is the right one to use for this particular scenario. That might be the topic of a webinar in 2024. But suffice to say, the log normal distribution is really useful at describing time to failure or cycles to failure for fatigue. And when you use a log normal distribution in a logarithmic scale, it creates a bell curve. So you can see on the horizontal axis, we have a log normal scale and a bell curve up top to sort of characterize the distribution of time to failure. And so the log normal distribution is made up of two parameters. One is mu subscript tau, the middle logarithm 10.23 becomes that parameter. And because this is now the bell curve, we can then work out, we know that 90% of all normal random variables are within 1.282 standard deviations away from the mean. And we know there's a difference between 11.06 and 9.40 of 1.64. So 1.64 divided by 2.564 standard deviations allows us to estimate standard deviation for this bell curve is about 0.6396. And that becomes our second parameter for our log normal distribution, which creates this curve here. And I know I just spouted a few numbers at you, but again, full description of the log normal distribution is outside the scope of this conversation. But this is what the log normal distribution looks like based on that analysis, assuming that the 500 megapascals is going to describe our typical stress our door handle is going to experience. And maybe, if enough of you ask, the log normal distribution might be a webinar I run next year. So here we have a curve which sort of characterizes the time to failure or cycles to failure for our door handle based on a 500 megapascal cyclic stress if the door handle is made out of 1045 steel. And that might be all the information you need to make a decision. However, we're not here to admire a problem. We are here to make things reliable. So does anyone know what things we can do to limit the likelihood of fatigue in our door handle? Please feel free to throw some ideas about what can we do to our door handle to limit the likelihood of fatigue happening. Use those very strong fibers. Round that corner for stress reduction. Stronger material, two good ones. Add mass, so make it bigger. Increase strength, so stronger material. Lots of good answers. So when it comes to fatigue, there are lots of different things we can do. Reduce stress concentrations, thicker components. So let's look at some of the top ways you can reduce the likelihood of fatigue. And you guys have got a ton of them. Reduce load. That's all well and good, but you can't ask your customers to be careful when they're turning their handle. That's not a good marketing point. So what we can do, though, is if you're talking about reducing load, you might be able to, as opposed to asking customers to be more careful, place a rubber stopper or dampener to limit the magnitude of stress. So when the person opens the door, they don't come up to a hard stop, which is where that sort of shock stress is generated. Increase the handle cross-section near the shaft. Shot peening. Now, shot peening essentially means we fire teeny tiny metal balls at another metal surface. And the reason we do that is because that essentially pushes the metal surface in, which creates pre-existing compressive forces, which make it very hard, or at least harder, for a crack to start growing. So shot peening essentially compresses the surface layer of a metal, which makes fatigue difficult to occur. And you often see shot peening applied at weld sites. So when someone's welded, or when you weld one piece of metal to another, which is a natural local area of weakness, you can do shot peening around that weld to try and create surface compressive forces, which make cracks harder to grow, to try and minimize the likelihood of fatigue. We can also increase inner radius. We can polish the surface, so we are less likely to have surface cracks. Material selection gets stronger a stronger material, decrease manufacturing defects. So a ton of the suggestions you came up with are on the screen right now. But this now brings us to the bottom of our tree with all these questions. We talked about fatigue. What is my system doing, not doing? And we looked at what does a broken bit look like? How did it break? The answer to that question is a failure mechanism. The next question we haven't asked ourselves yet is what started it? The answer to that question is what we call a fault, the immediate cause of failure. The immediate cause of failure can be absolutely anything. So, for example, the immediate cause of failure can be a stress concentrators. We just looked at this. We actually came up with some ideas to minimize the likelihood of fatigue. So stress concentrators, also called stress raisers or stress risers, points of a component where stress is increased primarily due to geometry. This is an example of a fault that might cause something like fatigue to occur, and that is usually the failure site for fracture, both overstress and fatigue. So this is one example of a fault. A defect is another example of a fault. So here's a defect where, or lots of defects actually. This is the molecular or atomic lattice within a metal alloy. You can see down here we have a grain boundary where the lattice of one structure is up against the lattice of another. You can see you have a dislocation, a line defect. We have a vacancy where we're missing an atom. We have an impurity where some other some sort of contaminant was allowed to enter our metal while we're manufacturing it. We have a substitutional atom where, as opposed to having our expected atom for our alloy, it's replaced by something else. And of course, there's lots of other things that can create defects. And beyond stress concentration and defects at the lowest level, we have lots of other faults that might ruin the day of our system. So, for example, if we look at an electric motor, an example functional failure mode might be the shaft won't turn. An example physical failure mode that might explain that functional failure mode is that the shaft has fractured. Why did the shaft fracture? The answer to that is the fatigue failure mechanism in this case, which allows you to see how we are able to link functional failure modes all the way down to failure mechanisms in the sort of quest to understand why this thing happened. The answer to the question, what started it, is the fault. The fault is going to be any number of potential reasons: misaligned bearings or gears, defects, surface imperfections. Misaligned bearings or gears increase the local stresses, which means even though your shaft might be perfectly manufactured, if the bearings or gears are misaligned, the stresses increase or are not what you expect. Therefore, your thing is subject to fatigue. And so these questions allow us to get to the bottom and ask ourselves, what did we do wrong? Or if we're not comfortable being that humble about ourselves, we might ask ourselves, what do we need to do? The answer to the first question is the root cause, the thing we messed up. The root cause has once you know the root cause, you can get a corrective action, which will help you essentially get that issue out of your system. A corrective action is a fix that involves a change to the design, operation, maintenance, or the manufacturing of your item to improve its reliability. So if we're looking at a failure scenario where the shaft won't turn because the shaft is fractured, the physical failure mode, the failure mechanism of fatigue, some potential faults are listed as you can see on the screen right now. If we put all this together next to our tree of failure, look what we get. Here is our failure scenario. A shaft won't turn due to shaft fracture from fatigue cracking caused by surface imperfections. This makes it really easy to work out what we need to do moving forward in order to make this failure unlikely to occur in the future. And some very basic corrective actions could be research and create a good upper specification limit on surface cracks. Maybe conduct a process for me to ensure that these surface imperfections, these surface cracks, are with a less than 0.05 millimeters, ideally even less. We call these words here, when we combine them, a root cause statement. Now, the root cause statement will, when you do it well, will help you find the root cause. Now, if we're going to go back to the tree, which has these questions, I can see that Shafat asked a question: is this method of finding the root cause similar to the 5 why method, asking whys until you reach the root cause? This method sounds more focus specific than simply asking whys. One of the biggest issues with the 5 whys is that the way it is taught, or way it's essentially perceived, is that you have one answer to each question. Why did this thing break? Because of fatigue. Why did the fatigue occur? Because of surface imperfections. Why the surface imperfections? So on and so forth. That's all well and good if you're doing that in a very informal way. But what we're trying to do here with these questions is actually have more than one answer for each one of these questions, and you run down each one. So, for example, if you got to the point where you realize that your shaft has failed due to fatigue, what started it? It could be a surface imperfection. It could be misaligned bearings or gears. It could be something else. And the idea is that there might be multiple answers to these questions, and 5 whys, the way it's taught, essentially almost requires you to have one single answer as you go down to one and only root cause. So it's very focused, and often people choose their favorite root cause as opposed to their to the full raft of root causes they might have to address. Carl's asked a few questions too. Let's talk about some of those questions Carl has asked. All products fail over time and use. That is why we need to put time and estimated conditions on use on products. Any thoughts? Of course, we do need to do that, Carl. We also need to take into consideration the corner cases. We don't want to design our handle for our lock for the perfect customer. We want to design it for the 99th percentile, or whatever the appropriate percentile of customer you can think of, which is why you might want to make sure that your 500 megapascals is not based on the perfect customer. It's based on the most robust or angriest customer. And perhaps ideally, you might be able to look at your most robust customer and say, okay, what is the stress that our most robust customer is going to put on our handle? Is there a way we can make sure that stress is below the endurance limit to make sure that fatigue never occurs? Carl also asks, it appears that failure mechanisms are innumerable for products. Any thoughts? Well, they're not innumerable because there's only a finite number of them. There's only a finite number of ways things can fail. But that said, there are so many that they might appear to be innumerable for us. So yes, there are lots of different ways things can fail, but the good thing is, because we are human beings, we know virtually every way our things will likely fail. Even when it comes to space disasters, the space shuttle catastrophes, those spacecraft which didn't do what they needed to do when in outer space. It turns out they weren't randomly attacked by aliens or weren't hit by some asteroid or anything like that. Virtually every single spacecraft that has failed due to a well-known failure mechanism, which means that we should have no excuse for earthbound products as well. It just means we need to critically think. Any thoughts about using computer simulations to identify the rate of fatigue for products? Love it. There's no reason you have to design or create a component in order to work out the likely fatigue weak points. Most CAD programs have some rudimentary, or not even rudimentary, quite sophisticated finite element analysis capabilities built in, where you can almost understand fatigue completely before you even think about manufacturing it. Any thoughts about insurance underwriting on the rate of rate of failure in products? I mean, lots of thoughts. I don't know how I could answer that in this webinar. It'd be a webinar in its own right. But I think that question needs to be a bit more specific for me to be able to answer it. But the reality is, most insurers are not full of the engineers that they would need to have in order to understand the likelihood of failure for your products. So it's very high level in general. Any thoughts about the 3 stages of fatigue failure? You're talking about low and high cycle fatigue as well. So just so you know, there are not all fatigue failure mechanisms are the same. Some fatigues are what we call low cycle fatigue, which behave in a very different way. And when we say low cycle, we talk about cycles in the order of 10s to 20s to 30s, so to speak, before they transition to what we call high cycle fatigue. The behavior is very different, but as a rule, low cycle fatigue is quite rare. In the real world, it usually happens when you don't expect fatigue to happen, because your stresses are higher. I think that's, again, fatigue, the 3 stages of fatigue. It's a bigger conversation, more boring conversation to have. But yes, there is differences between low and high cycle fatigue. If you're going up to 20, 30 cycles, as a rule, it's low cycle fatigue, and you need to use a different model. The SN chart might not be the way to go. And the high cycle fatigue, the SN charts are very, very useful. Sarah asks, is applying the log normal distribution also suitable to fatigue caused by interior initiated cracks? And the answer is, as a rule, yes. Now, you should always confirm this, but if I go back to the SN chart, let's go here. Whenever you see a model like this, where there appears to be a logarithmic scale creates, let's go to the next slide, actually. A logarithmic scale creates straight lines. As a rule, and when I say straight lines, I'm talking about the straight line at the very start. You can see that slope at the start, and you can see that straight line at the bottom. As a rule, the bit that goes across is going to be modeled by a bell curve. So let's actually go to this one here. So the horizontal axis, the scale is the logarithmic scale. We're still modeling fatigue where there is a relatively straight line in this logarithmic scale chart. And as a rule, the bell curve is really, really useful for modeling that. Now, because the scale is logarithmic, therefore, the log normal distribution will model cycles to failure relatively well. So as a rule, the log normal distribution is really good at modeling most fatigue scenarios. That said, if your profit margin depends on it, you might want to just double check. But your best guess, log normal distribution is, as a rule, a wonderfully accurate first guess. If you're that close to, if your margins are that close, that any deviation away from your best guess is going to be economically disastrous, you might want to confirm / do some more modeling to get there. But yeah, the log normal distribution does a good job of most fatigue scenarios. Bill writes, in applications where there are many physical locations where a crack might initiate and grow, such as bearing, gear, or wire, there is a physical motivation for the Weibull distribution. And the Weibull distribution, a bit of background, can model things that wear in, wear out, and do lots of other things. And in fact, the Weibull distribution can model, can mimic the log normal distribution very, very well. In many cases, what is modeled well by the log normal distribution can be almost as well modeled by the Weibull distribution, because the Weibull distribution does such a wonderful job at mimicking other distributions. Now, when it comes to, let's talk about bearings, for example. Fatigue is a nasty little failure mechanism. In my previous webinar, I looked at spalling on bearings, which is actually all about fatigue, but there's actually a couple of different types of fatigue, which creates little pits, and those pits grow over time, then creates spalling. So fatigue is at the root of that failure mechanism, but in practice, the way that those failure mechanisms combine with those rolling balls and everything else creates this phenomenon called spalling. So even though fatigue is at the heart of spalling, spalling has its own unique characteristics, which means that you can pick them up on probability distribution. So we know spalling is often modeled with a Weibull distribution of 2.2 or something similar. For people whose eyes are fading over or glazing over, I should say, because now I'm talking about probability distributions, feel free to look at some of the other webinars I've done on the Weibull distribution. But yes, Sarah also goes back to asking about the Weibull distribution. The Weibull distribution is always a good first guess as well, regarding how it's modeling how things fail. A log normal distribution or a Weibull distribution with a shape parameter is between 2 and 3 is a really good best guess. But the reason why I'm talking about the log normal distribution for fatigue is because it's based on the premise of things multiplying together. And we know that fatigue cracks tend to grow in a way which multiply over time, which is why we see the log normal distribution so useful in modeling fatigue cycles to failure. But have I touched off on your comment, Bill, and answered your question well enough, Sarah? No worries. All right. So what I'm going to do is go. Thank you, Sarah. I'm going to go back to the tree of failure with the questions we asked. Fatigue is a failure mechanism. It's the answer or potential answer to the question, how did it break? Fatigue is not the root cause of failure, but if you know what the failure mechanism is, then you can all, before you even think about modeling it, come up with wonderful ideas like shot peening or stress concentration or using a different material or understanding the endurance limit to essentially make sure that fatigue never happens. So too many people get caught up when it comes to fatigue, just simply modeling it. So we know how long it takes for something to fail. But if you know the failure mechanism, or you have an idea of what the failure mechanism is, first thing you should do is to look at what starts that failure mechanism, and is there anything we can do to get those faults out of our design. But hopefully you have learned something about fatigue. It is an infuriating failure mechanism in that it is one way of a structural member failing when it's subjected to multiple stresses below its strength over time. Aluminium or aluminum is particularly prone to fatigue. It will never stop suffering from fatigue, no matter how low the stresses are. But when it comes to steels, there is an endurance limit below which fatigue will not occur. So if you are able to design something where everything is below the endurance limit, you are good to go. So hopefully this is a cool high-level introduction to fatigue, and it's very important to understand where it lies within the causal chain of failure. It is not a root cause. It is not a functional failure mode. It's not a physical failure mode. But if you get the root cause statement right, you will find the root cause of failure, especially failures that haven't occurred yet, so you can make sure your first design is a reliable design. Are there any more questions before we take a well-earned break for 2023 and reconvene next year for our next series of webinars? See, Kevin writes that a lot of software tools help you identify the right distribution. Absolutely, they do. Thank you, Brent. Thank you, Shafat. If that's anywhere close to the correct pronunciation of your name, I apologize if it's not. Thank you, Mahendra.
Hey, Chris, I'm going to come back to Kevin's question, is that, and compare it to Bill's, is that the software doesn't understand the mechanism that the data that it has represents. So if you have bearings and you have scant data, or the software packages may pick a random distribution essentially because they have very scant data, or they have data that fits a gamma just slightly better according to some goodness of fit type deal. But we know, as Bill mentioned, is that bearing failures and gears typically have a phenomena of many, many points of failure. So there's balling going on, but it's happening at thousands of locations. And the Weibull distribution is kind of built to describe that kind of phenomena. Same as the log normal on a fatigue or crack growth type situation. Is there's fundamental multiplicative event going on there, and normal distribution is an additive event. So some things make it go faster, some things make it go slower, and that adds up. So understanding how the distribution actually describes the phenomena that's occurring is not done by the computer. So I always use those wizards with a grain of salt, because if you have a phenomena that is best described by this first principles, the way, like you're saying in log normal, it's the multiplicative phenomena that's occurring. Within log normal is built to do that kind of thing. So I hesitate to recommend using the wizards unless you have no phenomena that you can describe and you're just kind of trying to understand the data set. They have limited utility, is what I'm trying to say.
So, for example, if you have 3 data points for something, a bearing, which you know is failing due to fatigue or a fatigue-related phenomenon, and your wizard suggests that the exponential distribution is the best fit, you probably shouldn't go with that, because you now know from this webinar the log normal distribution is going to be more likely. And the exponential distribution describes something which doesn't accumulate damage. And fatigue is a classic failure mechanism as an example of how you accumulate damage, because that crack gets longer every single time. So I think just to echo what Fred's saying is, don't just put numbers in, get a wizard to tell you what's going on, and then make multi-million-dollar decisions based off those 3 data points and said wizard. Is that about right, Fred?
Yeah, no, I'm thinking of when I first showed the wizard to a professor I was in the classes I was taking at the time in statistics. He kind of stepped back and said, "Oh, that's just evil. You can get whatever answer you want now. What do you need to understand it for?"
Yep. But if you do a wizard and you get a log normal distribution fitting your data, and you reasonably suspect that fatigue might be causing your thing to fail, then all of a sudden you now have evidence that backs up your critical thinking regarding fatigue, which you can then use to make even more informed decisions. If you get a distribution which doesn't gel with your critical thinking best guess, then you need to take a couple of steps back and work out what's going on. But you don't want to organ grind those numbers in and out.
No, exactly.
Any more questions before we call it quits for today? I think we're done, Fred.